You are given an undirected graph that might or might not be connected. So it might have several connected components like so. This is one connected component. This is another connected component. This is the third connected component, and so on. In fact, this graph can even have cycles. So this could be one cycle, this could be another cycle. So this is just a general undirected graph with or without cycles and with or without connection between all the vertices. Now, in the traditional graph problems, you will recall that if the edges are weighted, suppose the weight on this edge is W1, weight on this edge is W2, and if this is node U and this is node V. So how do you define the cost of a path? Like if you have any path that originates from U and go and land at V. So you can see that the path from U to V encounters W1 and then encounters W2H and then reaches V. So this is one path. How do you define the cost of a path? It is basically the summation of Wi that you encounter on your journey. So cost of any path is sum of edge weights along that path. And how do you define the distance between U and V in the traditional sense in graph theory? You will remember that distance between U and V is the minimum cost of all paths. So it's the minimum cost of all paths from U to V. From U to V. For example, this is one path, but there could be another path. Suppose this is x1, this is x2, this is x3. Then you can see that there is another path that goes from U to V, and that path is x1 to x2. Sorry, I should write the edge weights on top so that you don't get confused. So that path is starts from U, encounters x1, encounters x2, encounters x3, and then encounters W2, and then finally meets V. So this is another path. And what will be the cost of this path? This will be nothing but x1 plus x2 plus x3 plus W2. Now, if this sum is smaller than W1 plus W2, then of course this will win. And this is the smaller cost path. So that's why the distance between any two nodes in a connected or maybe unconnected undirected graph is nothing but the minimum cost path across all possible paths that exist from U to V. And you know that you can compute this via Dijkstra's algorithm if all the edge weights are positive, or via Bellman-Ford's algorithm if there are no negative cycles in this graph. Now, in this problem, we are changing the definitions a bit. We want to say that we will still define the cost of a path and we'll still define the distance between two nodes. But we say that the cost of a path, this time we'll say that suppose your path goes from W1 to, let's formalize this. We say that suppose your path originates from you and encounters these edge weights W1, and the second edge weight that it encounters is W2, third edge weight is W3, fourth edge weight is W4, and the fifth one is W5. And eventually it reaches V. Then we define the cost of this path not as the sum of all the edge weights, but instead you create a set and you store all the Wi's that you encountered on your path, and then you compute the MEX, which is the minimum excluded value from this set, which is the first non-negative integer that is missing from this set. In other words, if you were to uh, plot all the Wi's on the number line, and suppose this is 0, this is 1, this is 2, this is 3, this is 4, and so on. And every time you encounter a wi, suppose wi is equal to 2, you color this in blue. And then w3 is equal to, like, let's say 4, you color this in blue. w5 is equal to 0, you color this in 0. w1 is equal to 3, you color this in blue color. Then the first uncolored box that you see on this number line, that is your gap. That is the first gap that is created. We call that as a MEX. And the cost of this path is equal to the MEX of this set, where the elements of this set are the edge weights that you encountered in your journey. This is the cost of a fixed path. But then you also have to define what is the distance between u to v. So this definition will keep the same as earlier. We say that the distance between u to v is the minimum cost path across all paths. This means that the distance between u to v, so the distance between u to v is defined as what is the minimum max on all the paths. So this is one path, this will have a max, call it A. This is another path, this will have a max, call it B. And if A is smaller than B, then we say that the distance between u to v is A. So you have to solve two questions. The first one is you have to answer these two questions. The first question is, what is the pairwise distance between any two vertices that I give you? I will query u comma v, and you have to print the minimum cost path. And the second question that you have to answer is, the original graph had n nodes. If I were to select a subset of these n nodes and only limited set of these n nodes, and I want you to add as minimum edges as possible to make this entire thing connected, and adding an edge between u to v will cost it will cost you distance between u to v in the original graph, which is basically the minimum max across all possible valid paths. So how do you solve this problem? So this is the problem setting. Now in this video we'll look at some techniques that can help you to solve this problem. These do not have an explicit name, but are very useful in solving graph related problems, especially the ones that have been appearing in AdCoder and Codeforces recently. So let's start by looking at the first question, which is, how do you compute the pairwise distance? And while doing so, we will learn a lot of things about MEX, and a lot of things about how to find the minimum cost to make something connected. So first, let's see how do you compute the pairwise distance. So instead of trying to compute the pairwise distance for everything, let's fix two nodes u and v, and ask the question, what is the distance between u and v? So for this question, you need to find out all the paths from u to v. There could be multiple paths, and then you have to take the minimum XOR. Now, of course, we cannot enumerate all the paths, that will be too costly. And here Dijkstra cannot help you, right? Because Dijkstra relies on the fact of summation, like summation of wi. So on every path, like, you cannot apply that. So Dijkstra only works because of a certain inequality that holds, right? So that's why you cannot apply Dijkstra here. So how do you compute the distance between u to v? Because see, another argument for why Dijkstra might not be optimal. So in my previous video of longest increasing subsequence, you must have remembered that Dijkstra relies on the one simple fact that the shortest path of a shortest path are also a shortest path. This means that if you are going from u to v and you encounter this node on your journey, which is, like, let's say an x, and then you take this node as your pivot, then this means that if you want the shortest path from u to v, then you should take the shortest path route to u to x, and then shortest path from x to V. But once MEX comes into picture, then this logic might not be true, because taking the shortest here greedily and then taking the shortest here greedily, it might actually increase the overall MEX. So we have to come up with a strategy, or like maybe a brute force strategy. Even though if it's not optimal, we have to come up with a brute force strategy to solve this problem. It should be correct even if it is a bit slow. So how do we do that? So to do that, we will use some observations regarding MEX. Now, if you have a set that contains n integers, then what is the max possible MEX? So regardless of what integers does it contain, you will realize even if it contains integers as big as infinity, MEX only cares about the first gap that appears when you arrange all the numbers from 0, 1, 2, 3, 4, 5, and this is n. So if there are n integers, so you can see that one integer can only fill at most or exactly one gap, or at most one gap, because if the integer itself is bigger than n, it is not really filling any gap. So the best that one single integer can do, it can fill one gap here, etc. So you need at least n elements to fill, n plus 1 elements to fill all these gaps. But if you have any element that is missing, and but the total number of elements that you have is n, and to fill this entire gap you need n plus 1 element. So even if all these elements tried their best, they cannot fill all the gaps from 0 to n. This means that no matter how big the numbers are, MEX of a set of n integer is always less than or equal to n. Therefore, in the original graph, suppose this is u and this is v located over here. In the worst case, how many edges will you traverse? You can only traverse the total number of edges that is available to you. For example, if this is a line graph, then what is the size of the set? That is simply E. E is the number of edges that is given to you. This means that the cost of all paths from U to V, it cannot exceed this E, where E is the size of the edge set. Okay, so this is one observation. But how do we compute the minimum cost? So even before computing the minimum cost, let's figure out how do we compute the cost when the path is fixed. So one naive algorithm to compute the cost when the path is fixed is that you collect all the edge weights, and then you put them into a set, and then you use your traditional MEX finding strategy to find out the MEX. But if you want to consider all the paths at once, we will apply a trick, and this is what I was talking about in the earlier part of the video, that there are some tricks using uh, which you can reuse for future graph related problems as well. And that trick is, uh, I'll show you a simpler version of that trick first. uh, you are given a graph, you are given a graph, and this could be, like, let's say it could have cycles, it could be disconnected, and so on. So this time I want to ask you a very simple question, which is, given a graph, is there a path between u to v such that all edges on that path are less than or are less than or equal to x? I want to ask this simple question. Now, some of you might know that this is a very standard trick, but for some of you, it might be completely new. So that's why I'm describing this problem first. So given any graph, undirected, may be connected, might not be connected, might have cycles, might not have cycles, but it is undirected graph. So now you have to find out, is there a path between u to v such that all the edges on the path are less than or equal to x? And what is the trick? So you create a new graph, and the trick is to move from weighted to unweighted. So you create a new graph, and we are well equipped to solve problems on unweighted graphs. So you have to do this transition from unweighted to weighted. Transition from unweighted, sorry, from weighted to unweighted. You go from the weighted version to unweighted. And how do you do this? So you know that in your resulting path, any edge that is strictly, that has weight strictly greater than x, they are forbidden. So in this new graph, you exclude all the edges, you exclude all the edges whose weights are strictly greater than x. So once you have created a new graph, then it might look something like this. Some of the edges are missing. So if some of the edges are missing, it will split it into further connected components. Like this connected component, this cycle itself could break. This could break and this could break. Why? Because this is greater than x and this is also greater than x. So this could become a lone isolated vertex. So this means that now you have another connected or might not be connected undirected graph, might or might not have cycles. But notice that in this version, in this graph, you can ignore all the edge weights. Why? You can ignore wi. Why is that? Because the problem is only asking you to find the path such that all the edge weights are less than or equal to x, and in this graph all the edge weights are indeed less than or equal to x, because we have discarded everything that was greater than x. Therefore, all the edge weights are actually equivalent, because the problem is not asking you to minimize the path or something, right? It's just asking you whether a path exists between u to v such that it contains all edges on the path that are less than or equal to x. So therefore, in this graph, if u and v are actually in the same connected component, if there is a path between u and v, this means that all the edges that it traverses, they will have weights less than or equal to x. Why? Because if any of the path, if any of the edge on this path had a weight greater than x, they were already deleted from the graph. So this means that this problem of this weighted graph of computing something where all the edge weights are less than or equal to x, that simply becomes another problem of finding out whether two nodes belong to the same connected component or not in the undirected version after you have removed all the banned edges. So these edges are banned or forbidden. All the paths that we have created must be with the edges that are less than or equal to x. All the greater than x edges are forbidden. So this is a very nice transformation that can be very useful in a lot of problems. And in fact, when you see this pattern, something is less than or equal to x, you will immediately recognize that in a lot of binary search related problem also, this trick could be helpful. So I think I did solve a good problem on this technique where you had to apply some binary search and then delete all the edges that are greater than x, and then figure out the connectivity and then repeat login time. So if I'm able to find it out, I will link it in the YouTube description. But if someone else already has that problem handy, do let me know. I will pin that in the comment section. So anyway, this was for the technique. Whether you want to know, when you want to know whether there is a path such that all the vertices, all the edges on the path are less than or equal to x. So can we apply a similar trick over here in the MEX related problem? Now, suppose you have MEX, suppose you want to consider whether this MEX is equal to M or not, whether the MEX of all integers on this path is equal to m. So if this is the case, then in your original graph that you have, this is your original graph, you can do one thing. Let's delete all the occurrences. So if this is the MEX, then it should not appear on the path, because if m starts appearing on the path, then when you are creating your number line to fill in all the gaps, and suppose this is m over here, then if m appears on that path and you actually take that m, then you will already fill this gap, so the MEX cannot be m. So in this version, you have to delete all the edge. So you delete all the edges with weight m. Delete all edges with wi is equal to m. Now, like I said earlier, that if m is deleted, then all the paths that you take, suppose this is the slot for m on the number line, then if u and v are still reachable, now see, now after deleting all the edges with weight m, you can convert this to an unweighted version. Why is that? Because now you are freely allowed to take any way, any edge, because none of them will contain m. Now let's see if things are as simple as just checking the connectivity. So suppose if u and v are indeed connected, so can you say that their MEX is m? Actually, this is not true, because this gap will still exist. Like you have found one path, where the MEX, where this gap exists. But what is the guarantee that there is no gap here? There could be a gap here as well. In fact, there could be a gap on the right hand side as well. But you can see that even though you cannot claim that the MEX will be equal to m if u and v are connected in this reduced version after deleting all the edges uh, with weight m, you can still conclude that the MEX has to be something on the left hand side of m. It should either be m or it should be something that is smaller than m, because it cannot be greater than m, because you have just found a path that misses m. So, and I already told you earlier that the definition of distance is the minimum cost path, right? So the cost of this path will be less than or equal to m. It will not be exactly equal to m. It will be less than or equal to m, because you have not taken m. It means you have created a gap over here, but there could also exist a gap over here as well. Suppose this is 2 and this is 5. It is possible that on this path 2 does not appear, but it's also possible that on that path 7 does not appear, but it doesn't matter, because MEX is the first element that is missing. Now you might immediately see some ideas originating. That is, you can now kind of apply a binary search technique to find the answer. So suppose this is your m, this is your midpoint, and that's why it was labeled as m, and this is also your MEX. Then you will see that if u and v are connected, suppose you are solving for u and v, if u and v are connected, after deleting all the edges, after deleting wi is equal to m, if they are connected, then you know that the distance between u to v can only be on the left hand side. So you can entirely discard the right hand side, because you have just found a path where the maximum cost, where the maximum distance could be at most m, or it could be something smaller, but it cannot exceed m. So this looks very promising, okay, but this also is incorrect, because every time you cut one part of the segment in half doesn't mean that you can apply binary search. And this is actually a very good idea. This is actually a very good example of why binary search doesn't always work. So I'll show you why this is not true. So binary search is not the correct idea over here, because sure, if you and V are connected, then you know for sure that you only have to look on the left hand side. But what if you and V are not connected? After deleting the edges, you and V are not connected, like they belong to the separate connected components. So if that is the case, can you discard the left half? Like if they are connected, then you were able to discard the right half. But if they are not connected, can you actually discard the left half? Because if they are not connected, they could not be connected due to two reasons. One is that there is indeed a path that has everything from 0, 1, 2, 3, 4, 5, etc. And maybe it was missing M, like it needed M to complete its journey, and that's why, and it was actually missing a bigger element X over here, and then it finally reached V. So if you delete this, suppose there is only one path, consider a line graph, basically consider a line graph like so, and all the nodes, they have all the edges, okay, and it goes from 0 to infinity, let's say. Then if you delete one vertex from here, which is M, then U and V will not be connected. But does and in this case, suppose this was the missing element over here on the right hand side of X. So this is a valid scenario. If the missing element is on the right hand side of X and you disconnect this M, then U and V are not connected anymore. But can the missing element be on the left hand side and still U and V cannot be connected? Yes, this can also be possible, because if this is the missing element and you have just removed this element over here, right? This was the connecting chain. Then if you have removed the connecting chain, like M was the crucial part of the path, like you had to cross M to reach V. So if you had to cross M but you deleted this M, you would not know whether the gap was created from here or the gap was created from here. So therefore, when you and we are not connected, then the answer is inconclusive. You cannot actually tell whether the MEX will be on the left hand side or it will be on the right hand side. So you can only tell that the MEX will be on the left hand side if U and V becomes connected. So that's why binary search will not be applicable over here. So if binary search is not applicable over here, what can we really do? So if you watched my previous video on contribution technique, and in that problem, I had discussed that there are different ways to interpret contribution technique. So in that video, we were talking about having several blocks, and you had to split an array into several blocks such that each block there are a total of k blocks, and each block has size greater than or equal to L. And in this problem, we had seen that when you want to compute the maximum, when you want to maximize the sum of any block, there was a very nice technique using which you can blindly assume this block to be the maximum value, and take all possible candidates, and then eventually you would have arrived at your answer. So I will link down that video in the YouTube description in case you want to watch it. But the idea originates, the idea of this part that I'm going to discuss, the idea originates from that contribution technique itself. So we have seen that every time you, so for a fixed M, every time you get that U and V are in the same connected component, right? Every time there is a path exists, the answer is less than or equal to M. This means that if you try out all M, then you would have processed all the candidates, just like the last video before. You have processed all the candidates. Therefore, one of these M has to be the answer. In fact, the minimum M, the minimum M is the answer. Now, why is this part true? Because For every m we just have the inequality that if after deleting all the edges with weight m, if the graph is connected, sorry, if u and v are in the same connected component, then you know that the answer is less than or equal to m. So why are we saying that if you try all possibilities of m from 0 to e, and why are we trying all possibility of m from 0 to e? Because we have already concluded that the weight of any path cannot be more than the length of the path, right? And the length of the path can be at most e. So that's why if we try all the max values from 0 to e, and then we take the minima for all the cases where u and v are connected after deleting wi is equal to m, then this minima will actually be the min cost path or basically the distance between u to v. But why is this true? Because notice that every time you get an inequality, sure, but consider the optimal path. Okay, consider the optimal path, and suppose this is the minima, this is the distance between u to v, and this is the answer is m star, which is the max, that is the minimum max. Then if you have tried all possibilities from 0, 1, 2, 3 up to e, then at some point of time you must have also tried this, and your answer would have been yes. Like when you tried this, if this is indeed the minima, then u and v would have been in the same connected component. But when when you would have tried anything that is smaller than m star, in that case you would have gotten your answer as no. Why? Because if the answer had indeed been yes, then how come there is a path that has a minima, that has a max smaller than m star, when you are claiming that m star is indeed the minima? So this means that trying everything and then taking the minima is will give you the distance between two vertices, and this is the second trick, right, that we have discussed. So in the second trick we saw that whenever anything is less than or equal to m, then if you try all the possibilities and then take the minima, that will give you equality. So this might be obvious to some, might not be obvious to others, so I'm just mentioning this in passing. Now I will talk about the third trick, which is, do you really need to try everything? Do you really need to try everything? Because eventually you are going to take the minima. So why not try it in an increasing order? So if you try in increasing order. So if you try to delete all the edge with weight 0, 1, 2, 3, 4, 5, etc., then the first time u and v get connected, that is your answer, is my claim. So you are now looking for first time u and v are in same connected component for, let's say, wi is equal to m, then their edge weight is equal to m. Then the distance, then you can claim that distance of u comma v is equal to m. And why is this true? Because of this statement. Like we said that we wanted to just retain the minima, but since we are iterating from left to right and so far we have not seen any connections between them, but at point 4 suddenly u and v got connected, it means that there is a path from u to v that has max less than or equal to 4. But we already tried everything that was less than or equal to 4, and in all of these cases u and v did not get connected. So this means that this is the first time they are being connected, so max has to be equal to 4. So this is the third trick. So in this manner you can see that for a given pair u comma v, you can iterate over everything in increasing order and you can compute their distance. So that's fine. But what if you want to compute for all pairs? What if you want to compute for all the pairs? Then you can notice that you just start deleting all the edges with 0, 1, 2, 3, 4, etc. And in each round, first of all, you delete all the edges with weight 0. And then you check which vertices became connected. Like this time, you're not fixing the vertices, right? This is the fourth trick that we are saying. This time, we are saying that we won't fix the edge. We'll just delete the edge. We won't fix the pairwise thing. And any two vertices that get connected for the first time, if it's their first time getting connected, any two nodes that get connected for the first time, then it means that there is a path between them with MEX M. So if it is the first time of them being connected, you know that their MEX is M. And if you repeat this for, like, if you check all the O of n square pair, whether they are being connected for the first time or not for each M, then you will eventually every pair will be connected at least once, or if they are not connected, it means that they are part of different connected components. That's fine as well. So this means that the first time they get connected, their max is equal to the M that you just encounter. So you can do updates of multiple pairs all at the same time. So the overall time complexity would become, you are processing E edges, you are deleting E edges one by one, and in each deletion you are checking all the n square pairs to check whether they are getting connected for the first time or not. So this solves the first part of the problem in n square into E. And that problem was how do you efficiently compute all the pairwise distances. Then let's talk about the second problem. It says that given a subset of vertices, what is the minimum cost to make them connected? So how do you solve this version? So suppose you are given a subset of edges, and let's say this is vertex 2, this is 5, this is 3, 9, 12, and this is 1. Then you know that cost of connecting 2 and 5 is equal to distance between 2 and 5, which you have already computed in the last step, right? And in fact, 2 can also be connected to 3, 2 can also be connected to 9, assuming that everything is a one connected component. If they are not, you can just assume the cost as infinity. And this is also connected over here, and this is also connected over here. So you can see that this graph will be a complete graph, right? Minus the, like, you can for now ignore all the edges that are not possible. Suppose 5 and 3 cannot even be connected in the original graph. You can still have an edge weight, but with, like, let's say cost as infinity. That's fine. So this is a complete graph, and it will have O of n square edges. But you have to find what is the minimal number of edges that you can take so that this entire graph becomes connected, right? So to make it connected, you need only n minus 1 edges, because minimum connection can be a tree without a cycle, because you don't really, cycles are a waste. Cycles just caught Cycles just add extra cost, and you could as well remove the edge of the cycle and the graph would still remain connected. So what you are looking for is creating a tree with the minimum cost, which is nothing but the minimum spanning tree, and this part is known as the minimum spanning tree. So how do you compute the minimum spanning tree of a graph? You can use the Kruskal's algorithm. So these are very standard techniques, so I will not dive deep into this. So this is known as the Kruskal's algorithm, and this algorithm basically says sort all edges in increasing edge weights in increasing weight, and then let me write down the text. Then Kruskal algorithm says that greedily taking smallest edge, or should we say, yeah, smallest cost edge that does not create a cycle will give you MST. So this is a very standard technique that you must already know, that Kruskal's algorithm, if you have O of n square edges over here, then you can start out by sorting all the edge weights. Suppose the edge weights are 2, 5, 9, 22, 100, and so on. So then you pick this edge and you compulsorily take it into your set, and suppose this edge is between this vertex u and vertex v. So you combine u and v into one connected component. Then you take this edge with weight 5, and if they are part of a different connected component, so suppose you had this u and this is u, this is v, and the edge with weight 5 is over here, like this is x and this is y. So you take 2 plus 5 in your set, and then you do this. Then this edge weight 9, if they combine two connected components like so, like if this is the edge weight 9, then you take it. But if they are actually between these two connected components, because there could be multiple edges between two nodes, or even if there aren't, then you could have something like this. So this and this are already in the same connected component, but taking this edge would create a cycle. So you silently ignore this edge. So as long as you don't create any cycles, by checking, you can maintain a DSU and you can check whether the nodes that you are taking are they part of the same connected component or not. If they are part of the same connected component, you do not take that edge, and this will give you an MST. So the problem was asking you to find what is the cost of that MST, and that cost of that MST is nothing but you create all that O of n square edges, you sort them, and then greedily take them while avoiding cycles. So how do we implement this? So you can see that first of all you have to compute the pairwise distance. So for that you start banning edges from 0 till up till size of the edges, right? Because the maximum max can be E. So you start banning all the vertices, all the edges, and in each round you create a fresh DSU. You call it the graph DSU, and if the edge does not have weight equal to the band edge, which is equal to m, you combine those into a one connected component, and once done, you find out in a single connected component, there will be multiple connected components that get created as a result. Then in every connected component, all the elements that join this component for the first time, they will have pairwise MEX equal to m. So that's why you collect all the elements in one connected component, and then you see, have they joined this component for the first time. It means that there is a path between them for the first time. If this is their first time, then you update their MEX, or basically the distance, which is equal to the bandwidth, since we are processing from left to right. So this is a very powerful technique, processing from left to right and then seeing whether things get connected on the first try. And then how do you compute the MST? So you already have all the distances, you take them, you sort them, and then you keep on greedily taking the edges as long as it does not create a cycle, right? So this unite function, it actually returns whether they were already part of the same component or not. If they were not part of the same component, then you take that edge giving this cost, and you try to finally see, the problem was asking you whether the graph will still be connected after doing all of these or not. So you just check this condition. So this way we have solved this problem in O of n square into E. And where is this time complexity coming from? Mod E for deleting all the m edges one by one, and in each deletion you go to each connected component and you check which edges, which nodes join these connected components for the first time. So can we do something better? Can we like solve this problem in O of n into E? And actually there will also be a log n factor over here. So this is O of n square into E plus n square into log n, because there are n square edges. But anyway, that doesn't matter. So can we improve the time complexity to something O of n into E? Can we do something better? Now you can skip the next part if this part of this video was already too much for you. you would have already gained a lot of insights about this. You can even implement this part. I will link down the problem in the YouTube description. So the next part also hinges on that same idea, that look at what you are trying to achieve. In the next version, this time they are not asking you to actually print the pairwise distance. This time they just want you to find the answer to this problem. This problem is out of the picture, that you only have to take a subset of vertices and find the minimum cost to make all of them connected. How do you do this? So you have to realize that what does your MST do? So your minimum spanning tree, that is the Kruskal's algorithm, eventually it will sort all the edges in increasing order, and then try to take everything that is not part of that connected component already, right? So this means that you don't actually have to run this algorithm to compute all the pairwise distance. You could just delete this edge. So you could start by just deleting edges from 0, 1, 2, 3, 4, 5, etc. And each time you delete an edge, right, it will create some connected component, etc. So suppose at this stage you have created these many connected components. Then you can notice that when you are deleting, when you are, suppose you have deleted this edge, m is equal to 3. So if you have deleted this edge, then some of these connected components might get connected, like you are now joining this component with this. This means that if this is being joined with this, regardless of which element is being from here, which element is being used from here, and which element is being used from here, their cost to connect them would be equal to k and would be equal to m, and it actually does not create a cycle. And in fact, this one can also join this connected component. So all you have to do is just simulate this MST algorithm, and you don't have to explicitly create all the pairwise distances, because every time two connected components get connected, then this means that even if you had the explicit edges with you, then you would have definitely taken that edge in your Kruskal's algorithm, because this is not creating a cycle. So the optimization is very simple. You just have the same code as before, like you had for banning the edges, this one. But this time you don't apply the pairwise edge computation algorithm. You just say that, okay, I want to ban this edge, a particular edge B. And then after banning an edge, you decide which nodes are still connected. Like you decide in the original graph which one of them are part of the same connected component or not, and then you maintain another DSU for the Kruskal's algorithm. So this is the DSU that you are maintaining for the original connectivity, to check whether two things are two things like U and V, whether they have a MEX equal to K or not, or whether they have a MEX equal to M. And you maintain another DSU that is tracking your Kruskal's algorithm. Now in your DSU, you want to, this time you don't actually have to iterate over all the pairwise things in your DSU. You just have to check, you just have to merge these DSUs, and you have to check whether they have been merged for the first time, right? So you split it into several components, and then you do the merging. So you can either add the cost as m, you can either increase the cost by this bandwidth when you are doing this merging over here, or if you want to be fancy, you could just do the merging right now blindly, okay? And then once you have done the merge, you can figure out if this merge happened in this round or not. So that's why you see that we do this merge in the graph DSU, and then we check whether in the answer DSU are they already part of the same connected component or not. If they are not part of that same connected component, it means that they are being merged for the first time. So if two components are being merged for the first time, they will incur this cost, and you increment this cost by 1. So this way you can actually simulate whatever the Kruskal's algorithm was going to do with all the O of n square edges, and you don't have to explicitly create them. So what is the time complexity? So this for loop, this goes till E, and inside this you are only, so you are only looking at all the elements inside this, right? You are only looking at all elements in a connected component, and you are saying how many of them have joined the component for the first time. So the overall, even though this looks like O of n square, because there is no 2 for nested for loop, but this is just like your adjacency list. So the time complexity is n into E. And in this manner, we were able to solve this problem and optimize it from n square into E to n into E. Now, of course, uh, when this problem appeared in the code forces round, they actually have a solution. They actually have a fancy way to even improve it further. Like we went from n square into E to O of n into E, right? There is actually, if you're interested, there is actually a way to go to, I think, n plus E into some log factor or something. And this can be done using divide and conquer and rollback DSUs. But okay, I mean, you don't have to learn everything in one go. Even if you got this idea of n square into E, like how the MEX works and how to apply that contribution technique idea that we had discussed. Like if you do not know a candidate, just process all candidate blindly and you will eventually have processed your answer. And then how processing MEX from left to right will always give you the minimum. So a lot of things that we learned. And even if you don't get an AC on this problem, which you won't because the constraints are only designed for n plus e into log, but I would strongly suggest you to implement this n square into e solution by yourself and n into e solution by yourself, so that you learn at least something from this video.